Section 10.4, this is a big one, secants and tangents. And this is actually 10.4a, because we're going to break this up into two videos. Okay, so here we go. Lots of definitions in this section. The first being the definition of a secant. So a secant is a special line that intersects a circle at exactly 2 points. So this right here is a secant line. So you can see how it intersects the circle at that point and at that point. Okay, so it's a line. It goes forever and ever, right? So it is going to go outside of the circle. Now the part that's going from this endpoint to that endpoint right there, that would be a chord, right? But once you start extending stuff that's outside of the circle, it becomes a secant line. The next definition is the tangent line, and that is a line that intersects a circle at exactly 1 point. So it has to be a line that is completely outside of the circle and only touches the circle at this 1 point. People tend to get confused by diagrams that look like this, where they would have a line, ooh, that's a bad line, but you get the idea, where they look at this and they say, oh, well, this has only intersected the circle right here at this point, and so therefore this has to be tangent. But that's false, because if we were to extend this, and it would go all the way out here, it does eventually intersect the circle at another point. So this is actually a secant as opposed to a tangent. Okay? So really be aware of that, the difference between the secant and tangent. Your tangent line is always going to be outside of the circle. It's never going to go pass anywhere through the interior of your circle. Okay? Now, some interesting facts about a tangent. The tangent line is going to be perpendicular to the radius when you draw it to that point of tangency. So point of tangency is this point right here. So whenever you connect the center to the point of tangency, those two lines are going to be perpendicular. Okay, so I can make a little perpendicular symbol there. Okay, now sometimes we don't deal with lines, we deal with segments. And the same rule follows, that the difference between the tangent segment and the secant segment is that the secant has to intersect it twice. Whether it shows it happening all the way through, or you could potentially extend the chord or the segment or the line to intersect the circle at 2 places. Whereas this out here, you can see, okay, it intersects at B, but if we continued on, it's never going to intersect the circle again. So that would be a tangent segment. Okay, and it still follows along the rule that the tangent segment and the radius are going to be perpendicular to each other. So those are the first couple definitions that we have. Let's move on. Okay, so we take a detour here into a theorem, Theorem 85, which says that if we have 2 tangent segments and they are drawn from a point, from the same point outside of a circle, then the 2 tangent segments are going to be congruent to each other. And this is known as the 2 tangent theorem. So yes, you could use this in a proof. So if we look here at these 2 segments, CD and BD, if you know that CD and BD are tangent to the circle A, then you're going to know that CD is congruent to BD. So 2 tangent theorem. And this only works with tangents, it does not work with secants. So had, this segment right here passed through the circle and it had been a secant, then this would not be true. Those 2 segments would not be congruent. All right, tangent circles. So circles that intersect each other at exactly 1 point. So it doesn't just have to be a line that's tangent to a circle. You can have 2 circles being tangent to each other. And there's actually 2 different ways that circles can be tangent to each other. So there's externally tangent which looks like this, and you can see that right here at point F is where they are tangent to each other. And then there's internally tangent, where you have one circle that's inside the other circle. And this smaller circle could be as big as you want it to be. I mean, it could go all the way out here, right? Or it could be really tiny. But you can see that the two circles only intersect each other here at point I. And so what's interesting is that if we were to draw in lines through the points of tangency and make them tangent lines, these tangent lines are going to be perpendicular with the line of centers. And there's a new vocabulary phrase for you, the line of centers. And I don't have this written down anywhere. But the line of centers is basically the line or line segment that connects the centers of two circles. So here it would be EG, and over here the line of centers would be HJ, and because it's a line it could extend out as far as we wanted it to go. So we end up having this tangent line perpendicular to the line of centers. Okay, so that will be useful in the future, I believe. Moving on. All right, so we have something called a common tangent. And that's when you take two circles, and they could be spread apart like you see here. They could be two tangent circles, or they could be overlapping circles, so almost like a Venn diagram. And you have these two circles, you can draw in a tangent line that's tangent to both circles. Okay, so tangent to this circle and tangent to that circle at the same time. And so those are called common tangents. Well, there's two different ways that you can get these common tangents. One is if it's a common external tangent. So that would be a line that would go kind of above the two circles and be tangent here and here. We could have drawn the tangent below. I don't know if I can do this freehand. Whew, not bad. So this would also be a common tangent down here. And this is a common external tangent as well. So it's one above, one below. Okay, let's get rid of that. So that's the common external tangent. Now, we could have also done a common internal tangent. And the common internal tangent, you have to do that between circles that are spread apart. You do not get common internal tangents if the circles are touching each other. So this is what a common internal tangent looks like. So it's something that kind of goes through in between the two circles. And you can see here's a point of tangency right there, and there's another point of tangency right here. We could have drawn in going the other way. I could have done, let's see if I'm good at freehanding this one like I did. Oh, that's terrible. Oh, okay, well, you get the idea. So I could have had this tangent be the common internal tangent as well. Okay, so why are we doing this? Well, what you're going to end up having to do is figure out the length of a common tangent, whether it's a common internal or common external tangent, segment. So from one point of tangency to the other point of tangency. So let's see how this is going to work. All right, so let's do this common external tangent problem. Now I'm just going to right off the bat mention that when you guys are doing these problems, most of the time the diagram is not going to be drawn for you, and you're going to have to draw it yourself. And the real key to being successful in these problems is making sure that you take the time to draw your draw your circles and your tangents and your line segments exactly how they should be. And part of that is going to have to understand the definition of tangents and what that means in their relationship with the radii. So in this case, this problem is already drawn for you. We have two circles, D and C, that are tangent to each other right here at this point. I've connected the two centers, so here's our line of centers. Okay. Here's our common external tangent, AB. And what I've also done is I've drawn in the radii from the centers to those points of tangency. And if you recall, by definition, we know that these need to be right angles. So when you're drawing your diagram, it would really be helpful. Ooh, that's terrible. I'll try to do that again. It would be really helpful if you draw these so that your radii look like they're perpendicular to your common tangent. And I would really make the effort of trying to make your common tangent slanted like this, as opposed to making this circle up here and a straight across. It's going to help you, trust me. Okay, I've been doing this for 14 years. I see all sorts of problems that students have. It's the same thing every time. They draw their diagram incorrectly. Okay, so we start off with that. The next thing that we're going to do is we're going to talk about these lengths. So if you look at here, BC is this length right there, and AD is that length right there. So that's 18, and this is 8. Well, those are the two lengths of your radii. Okay, now I know I have some animations here, and I can't exactly remember what I've put in, so let's see what's going on. Oh, look. Okay, we'll do that. Those look much better than my crappy attempts. Okay. So let's put in our measures of our radii, which are 8 and 18. The next thing that you want to do, and this is going to be really key for these common external tangent problems, is you need to draw in this segment. Okay, now you're going to always draw it in the same way. You're always going to start from the center of the smaller circle, and you're going to draw it towards the radius of the larger circle. So no matter how you set up your diagram with the circles and the common tangent and whatever, always know that the line that you're going to draw in is going to start at the center of the little circle and is drawn to the radius of the larger circle. And I really emphasize this because the problems that people do, the way that they draw their diagrams, they end up trying to start their line from this point of tangency, and they try to draw it like that. And it doesn't work that way. Okay, so when you draw this line in, what you're going to do is you're going to draw it in such a way that it is perpendicular with this radius. So that's why I have this perpendicular segment right here. And if you notice, if this is perpendicular, then this is also a right angle. And what kind of shape do you think that we have created here? Hopefully you guys are answering with the word rectangle. So this is a rectangle right here. And then on the other side, this right here is a right triangle. And if you draw this correctly and you put in all your right angle symbols and you pay attention, you'll notice that this segment DC is the hypotenuse. And this is where people run into problems, is that they end up thinking that the segment they drew in is the hypotenuse, and it's not. Okay? So now what we have to do is we have to figure out some lengths here so that we can solve for the length of this blue segment. Because if we know the length of this blue segment, and this is a rectangle, then AB is congruent to this segment, and then we'd have our answer. Okay. So because this is a rectangle and this has a length of 8, then from A to this point is also 8. And if this whole radius is 18 and this part is 8, then we can subtract the two and get this length right here, this part of the right triangle, which is 10. And now I know that 10 is a lot bigger than 8, and this looks a lot smaller, but we have to go by the numbers. Okay, the most important thing is knowing that this is a right triangle and that this right here is the hypotenuse. Okay, now here's the other tricky part. Now sometimes your circles are tangent to each other, sometimes they're spread apart and they're not, and sometimes they're overlapping. You have to figure out this length, DC. Some points, they give it to you. Some problems, they just say, hey, the distance between the centers is 32 units. Other times you have to figure out yourself. Well, let's think about this. The radius of this circle is 18, and the radius of that circle is 8. So can't we just add the two together and get that whole length being 26? Okay, so that works when the circles are tangent. So now that we have this right triangle, this length is 10, that length is 26. We have two sides. We can use Pythagorean theorem, or if we're lucky, we get a triple, which we do, and we now know that this is 24. This is a 5, 12, 13 triangle, right? And then if this is 24, then that's 24, and we've solved our problem. So AB has a length of 24. Okay, so I know I went through this really slowly because I know a lot of people have difficulty with these problems. So hopefully you can go back over that again if you need to. But we're going to move on to the next problem, which is the common internal tangent, which is a little different, kind of the same idea, but a little different setup than the common external. So remember how I said that with the common internal tangent, the circles must be separated from each other because you have to have this segment that can go through this middle part here, okay? So what that means is they're going to have to give you the length between the centers of the circles, which they did. They gave us that that length is 13. Now they've given us the radii. They tell us that AC is 3 and DB is 2. So what you're going to have to do is actually, in this case, draw in your radii. And remember that if this is tangent, that your radii, when you draw them in, should be perpendicular to this line. Same thing over here, the radius should be perpendicular to this line. So it looks like we get two little right triangles, don't we? Not that we're going to use those, but that's what your diagram should look like. So let's start placing in information that we were given. So we're given this is 2, that's 3, we know this whole length is 13. We're trying to find the length of CD. So remember how in the common external tangent problem I said that you're going to draw in this segment? It was the blue segment. And you're going to also draw in this case it's going to be blue again, but you're going to draw in another segment. And just like before, you're going to start at the center of the little circle, and you're going to draw towards the radius of your large circle. But we want it to be perpendicular to this line. So what that's going to mean is that this has to come out here, and we're going to have to extend our radius outside of the circle. So we're going to extend this out a little bit so that we can draw in our blue segment. And we want it to be perpendicular. Okay? So once again, if you notice, we've created a rectangle. Same thing that we did before, creating a rectangle. Okay? And because this radius is 2, this length in the rectangle from C to this point is also going to be 2. Which means that when we add 3 and 2 together, this whole segment is going to be 5. Now, this is interesting. I don't know if you can see it with all these lines, but right here we have a right triangle. You guys see that? Okay, that's going to be key because this is the right triangle that we're going to use to solve our problem. Because one side, one leg of that right triangle is the blue segment. And that blue segment is congruent to CD, which is what we're trying to solve. So if you look at this, with this being 5 and this being 13, that's the right angle, so we know that this is the hypotenuse. We can do our Pythagorean triple, and we know that this is 12. And therefore, CD is also 12. So we've solved our problem. Pretty cool, huh? Probably not. You probably don't think this is as fun as I do. Oh well, okay. Well, you're going to have lots of practice with these, so hopefully you'll get good at them. Sorry that this video was so long. Kind of makes up for those 2 short ones that you had, huh? Oh, 18 minutes. Sorry.